Right. Today's date. Whenever we are doing any work, we need to put a date there. Today we want to look at simple evidence for the existence of particles. Because the other time we were talking about the solids, liquids, and gases as composed of particles, tiny particles, which we cannot be able to see with our eyes unless we use very powerful cameras, microscopes. That's when we can be able to see. Now, those particles can either be atoms, they can be molecules, or they can be ions. So we have either atoms, molecules, or ions. I'll use water and sodium chloride to explain what ions are and what molecules are. Now, when I write H2O in chemistry, this one here means this is one molecule of water, and the molecule of water is made up of 2 atoms of hydrogen and 1 atom of oxygen. So we can have matter existing in form of molecules like this one here, or molecules like that from carbon dioxide, that is also another molecule. Or we can have it existing in terms of atoms. For example, this one here is an atom of hydrogen. Or this one here is an atom of carbon. This is hydrogen, this is carbon. Then we can also have matter existing in form of ions. For example, in sodium chloride, we have the negatively charged chloride ions and the positively charged sodium ions coming together or attracting each other to form crystals of sodium chloride. So we can have either the molecules like water is and carbon dioxide, or we can have atoms like hydrogen is and carbon, or we can have ions like sodium ions and chloride ions in sodium chloride. Now these particles are so tiny that you cannot see them using your naked eyes. But we can use simple experiments to show that actually they exist. Now, one simple experiment which I want to show you is here with me. I have 2 liquids. This one here is concentrated ammonia or aqueous ammonia, and this one here is concentrated hydrochloric acid. Now, when you open them, open the reagent bottles, if I open, you cannot see anything there. You can't see anything coming out of that bottle. Likewise, if I open this one here, you can see just a few particles coming out of that bottle. But now, if I brought these 2 bottles near each other like that, you can see what is happening. Okay, so those are particles coming out of those 2 liquids. Now, this one here, aqueous ammonia, is giving off ammonia gas, and this one here, concentrated hydrochloric acid, is giving off fumes of hydrogen chloride gas. Now, when we put them together, then they form those dense white fumes of a compound called ammonium chloride. This is as a result of ammonia. The ammonia reacting with hydrogen chloride. Hydrogen chloride gas. And when these two react together, they form the dense white fumes, which you are seeing as ammonium chloride. So that one is showing us that actually, even when we are not seeing those the particles, but they exist. Okay? Because when I opened this bottle here, you didn't see anything coming out of it. But when I opened the other one of hydrochloric acid, you saw some white fumes coming out, but they were not as dense as when I brought the two bottles close to one another. So that is one simple experiment which we can use to show that matter is made up of particles. Now, the second experiment which we can use is I'm going to use this one here. This is clean water. It's clean water. I want to put in some few particles of a substance that I'll explain later. I'll drop in some few particles of this substance here. And then I will expect you to observe what is going to happen with the time. Okay. Now it was clean water, but now when I put in that substance, you see what is happening. The substances or the purple color is diffusing, is moving from the point where it is concentrated to regions where it is less concentrated or where it is not existing at all. Okay? But eventually, when we leave this beaker for some time, we shall check on it before the end of the lesson. We shall see that the whole beaker is going to appear the way this one appears in this test tube here. Okay. This was clean water, but when I put in some crystals of potassium permanganate, this is what we saw. So this one is showing us that actually the matter is made up of particles. Now the one which I've done last. See, in chemistry we have symbols which we can use to represent the elements, the compounds, and ions. So if I want to represent this compound which I added here, we call it potassium permanganate. That is the compound which I mixed with water to form this solution here. Now, in chemistry, we may not bother writing all the whole of that name. So I can write a formula to represent this. So we normally represent it as, write the capital K, represent potassium, capital M. That one represents manganese, M with a small n, that is manganese, and then the capital O, that is oxygen, and when you put a 4 there, so that one is the formula representing what we call potassium permanganate. So it is the potassium permanganate which I added to this water here. Now eventually, the whole of the water in this beaker is going to turn to purple, just like you see this solution in this test tube. So this one means that the particles of the potassium permanganate were able to move from the region where it is less concentrated, regions where it was more concentrated, thereby forming a solution, and the whole the whole water in the beaker became colored, as we shall see at the end of the experiment. So that means that this potassium permanganate is actually made up of particles. So these particles enter into water, dissolve into water, and then the whole beaker containing water is going to turn purple because of that compound which is dissolved in it. So that is the compound that I've used. I've used potassium permanganate. In short, we can write a symbol or the formula, the chemical formula for it, which is this one here. But of course, we shall learn about chemical formulae later on. We don't need to bother about this one. Why we write the O here, why we write the capital M, the small m, and the capital K. We shall be doing it at a later time. But for the moment, I just want to show you that this substance here, when you add it to water, it dissolves in the water and it gives water that color that you saw. Right, so that is another experiment, simple experiment that we can use to show that matter is made up of particles. Now, these particles, which I said they can be atoms, molecules, or ions, we said at one moment that they are constantly in random motion. They are constantly moving. The only difference is that in solids, we said that the movement is restricted to vibrations within fixed positions. Whereas in molecules, the particles are able to move from one point to another. That is why you saw that the potassium permanganate particles were diffusing, were moving freely in that solution, and eventually we shall have the whole liquid covered as with the purple color. Right. Then I'll give you some time to think of any possible experiment that you as individuals you can also design to show that actually matter is made up of these tiny particles. I've given so far 2 of them, and there are more. Possibly I will add the 3rd one because this one is commonly seen when you are attending ceremonies. Let me say wedding ceremonies or parties, birthday parties, and what have you. You normally see people decorating the venue with balloons. Now, if you got a balloon and you blow air in it, in science we say if you inflate it, when you blow air into it, you are inflating it. So when you inflate the balloon and then you tie, let's say this is the power balloon, and then we tie this part here so that the air does not move out. The air that we put in does not move out of that balloon. Now, if you kept this balloon there for about 3-4 days, there is something that you'll notice. Now, you'll be able to notice that as time goes on, that balloon is going to keep on decreasing in size. Let's just I see some hand up. Yes, can you say what you want to say quickly and proceed? Aisha, can you say something? I see your hand up. Aisha, can you say what you want to say quickly and clearly? About Zoe? Zoe?
Teacher, I was asking the things of molecules and atoms. I didn't understand it properly. You said they are constantly.
Right. I said that matter is made up of these small tiny particles, which can be either atoms or molecules or ions. And I gave an example of what an atom is. For instance, we breathe in oxygen, or we breathe in air. That air contains oxygen. Now in chemistry, oxygen, we write it as, that is the name. However, when we write it with a symbol like that, or capital O, that one represents an atom of oxygen. And when we write it with a 2 as a subscript like that, this one here represents a molecule of oxygen. And I clearly said that we shall learn about atoms, molecules, and ions at a later time. But for now, just take it from me that this is the name of oxygen, This is the symbol for oxygen atom. This is the symbol for an oxygen molecule. And later on, we shall be defining what we mean by an atom, what we mean by a molecule, and what we mean by ions. We shall know that one, don't worry. But it does not prevent you from reading ahead. And also, possibly, let me do this. Now, all of you are seeing this piece of chalk here. It is made up of very tiny particles. So what you are seeing this as a piece of chalk, it has a multitude of those tiny particles. Now, supposing I say you identify or isolate just one particle of this piece of chalk, it will be very difficult for you, because I'll first of all break it into two, put one aside, then this one I also break it into two, then I continue this one, I break it into two. Now you can see that this one is becoming difficult to break. Okay? Now, even this one which I'm holding has got very many particles, very many indeed. Because we say those particles we cannot see with our own, with our naked eyes, unless we use a very powerful microscope. So it means that even this piece, however tiny it is, the one I'm holding, it has so many of those tiny particles. But now you saw that how I was struggling to get two pieces out of the piece of chalk that I had. It is even more difficult to now get two pieces from here. But now supposing, like when I'm using the blackboard, okay, when I rub, there are particles of chalk. There are particles of chalk that I can see them dropping. Okay? Those ones are quite tiny indeed. But however tiny they are, they cannot be the equivalent of an atom or a molecule, because those atoms and molecules are so tiny. Very tiny indeed. So all over, even our bodies are made up of so many things. Okay? We have blood, we have water, we have bones, and so many others. So all those are made up of either molecules or atoms, and also the ions. We have the ions in our bodies. So that is what. Now you shouldn't get scared about these terms here. We shall be handling each of them at a time. So just what you need to know is that when you break something, like a piece of chalk, like I broke the piece of chalk, when you keep on breaking it, time comes when you get very tiny particles. Okay? But even when you get a very tiny particle, that is not an equivalent of an atom. Because if it is an atom, you cannot be able to see it because it is too tiny indeed. I hope that is clear. Right, I was saying that we can also show that matter contains, or there is there is existence of particles in matter by using the balloon. So I was explaining something to do with the balloon. I said when they are making for you a birthday party, for example, you normally blow inflate balloons and then you decorate your room and your home. But when you watch carefully those balloons, if you put them there in the morning, when it comes to around midday, if it is a hot day, when it comes to around midday, you see some of them spontaneously bursting without touching them. You see them bursting. Okay? Now, why are they bursting? Because the particles which are present in the air that you use to inflate the balloon, those particles, when it becomes hot, they gain kinetic energy, and therefore that kinetic energy makes them move faster. So when they move faster, they tend to collide with the walls of the container more often. Remember, we said that these particles are already in constant random motion. Now, it means, therefore, that if the sun or if the sunshine gives them more energy, then they will become even more energetic to move randomly. And when they do that, time will come when that random motion or that collision with the walls of the container will make the walls of that balloon to give way, and therefore they will burst. However, some of them which do not burst, by evening time or by the following morning, the balloon which was of this size, you will find the same balloon has shrunk, and the size will be as small as this. Now, what explanation do we give to that? Now, the only explanation we can give to this is that this balloon, the membrane or the substance which is used for making that balloon, has got particles. And those particles are arranged closely to form that, because that one will be a solid. However, however much you arrange those particles, there is no way you can ensure that the spaces in between those particles are not allowing the air that you put inside the balloon to get out. Now, if you look at the notes that we, or the workbook that we gave you, there's a diagram which is showing the particles of air inside the balloon when they are penetrating through very tiny holes of the balloon and getting out of the balloon. That's why there is a reduction in the size you began off with a lot of air in the balloon, but as time goes on, the balloon shrunk in size because part of the molecules of the air that you put in are getting out. They are getting out of the balloon. However, as I said the other time, I said, if you put in the air when it is cool and make sure the balloon is properly inflated, when it comes to around the midday when the sun is hot, you'll be able to see some of them bursting on their own without initiating the bursting. Let's hear from Amar. I think she has something to say. Amar?
Teacher?
Yes, please.
Good morning, teacher.
Good morning.
Teacher, I wanted to ask, what if like that you said that the balloons in the evening when the sun comes out, they start to burst. What if the day is like cool? Like what if the day is rainy and there is no sun?
I remember I said that if it is hot, on a hot day, that is when the balloon will burst. But if the day is not very hot, it can stay even for 2-3 days. However, when you check on it, it will have shrunk in size. The shrinking in size shows us that the particles of air that are inside that balloon have found a way they are escaping from that balloon. Even when you have tied very tightly, tied the mouth of the balloon, but the walls of the balloon or the membrane that is used for making the balloon does not protect these molecules from getting out. Okay? Because it is a solid, and we said that in solids, the particles that make up that solid are compact or they are close to each other. But it does not mean that they don't have some spaces in between them. So eventually, some air will get out through those spaces. I hope that is clear. Right. So we are simply saying that why does the balloon burst? Because the air that you put in there has got tiny particles. Now, when the sun shines or the sun shines on those balloons, the particles of air inside the balloon are going to gain kinetic energy. Just like, for example, when you are hungry, you are not as energetic as when you have just had a very good meal. Okay? So even these particles, when they get when it shines on them, they get that heat, which gives them energy. And therefore, when they get that energy, they move faster. When they move faster, they collide with each other inside that balloon. Then they collide with the walls of the container of the balloon. And eventually, if that energy is quite sufficient, they give way. The balloon will burst. But if it does not burst, then it will shrink in size, like that. Meaning that you started with a larger mass of air, but because some of it has gone out, then you end up with a smaller amount of air inside the balloon. So that one is showing us that the particles or the matter is made up of particles. I just want to emphasize that what I'm calling the particles can be either atoms or molecules or ions. It does not matter when you do not possibly understand what an atom is. But I've just given you a picture. That if I started breaking this piece of chalk, even the smallest particle you get cannot be an equivalent of an atom. Because an atom, when it is one like this, You cannot even see it with your naked eyes. You can't. They are so tiny. Even when I have written this compound here is even when it is made up of many atoms chemically combined together. But when I isolate one of that particle, you cannot see it with your eyes. Okay? So we only need a very, very powerful microscope in order to observe some of these particles. Okay? But we are just doing experiments like the one I did. When I did this one here, this water, this was clean water, very clear water. But when I dropped in a piece of potassium permanganate, this compound here, the compound sprayed or moved from the area where I had dropped it. You can see what is happening in our beaker. Okay. I dropped the particles at the bottom, but now you can see the color is spreading slowly. It's spreading slowly upwards. And eventually, if we leave this experiment for the whole day, if you came back here tomorrow, you'll find that all this water will have the color which is purple, the way this one is. Because the potassium permanganate particles were able to spread, okay, spread from the bottom where I dropped them to other places in the beaker where they were not available. Now, that process where the molecules of a substance move from a place where they are highly concentrated to a place where they are less concentrated, that movement, we call it diffusion. We call it diffusion. It's the movement of particles of matter from a region where they are more concentrated or highly concentrated to a region where they are less concentrated. So the phenomena of diffusion is also goes a long way to explain that actually matter is made up of particles. Because if there were no particles, how do this color move in the water so that the whole body of water becomes colored like that? Okay. So this is part of the explanation that matter is made up of tiny particles. Right. I want to say something again about because we had looked at the heating curve and the cooling curve. I hope people didn't have problems with it, but I just want to refer to it briefly before we proceed. Now, when we were drawing the heating curve for water, we began with something like this. We began from a point. This is 0. This is possibly minus 25. This one is representing temperature in degrees centigrade. This is 10, 20, and 30, and so on and so forth. Then this one here is representing the time. This is the time. It will be in minutes, or it can be in hours. It does not matter. So when we are drawing the heating curve, we say if I begin with ice at minus 25 degrees centigrade and I heat it, what happens? The temperature of the ice will increase. Okay? Because when you are moving from a negative number to what's 0, it means the temperature is increasing. So a temperature of 0 is higher than a temperature of -25. So when we heat the ice, the temperature increases and reaches 0. Now, at 0 degrees centigrade, what happened? We saw that there was no change in temperature. The temperature remained constant for some time until all the ice had turned into liquid. That is when the temperature again began to rise. The temperature rose until it reached a temperature of about 100. When it reached 100, again it remained constant for some time until all the water had turned into steam, and then the temperature began to rise, the temperature of the steam began to rise. Like that. So that means that at this point here, and at this point here, we were adding heat to, here we are adding heat to the ice, but it's not manifested in the increase in temperature, because the temperature at the beginning, at this point, is the same as the temperature at that point. So which means between these 2 points, there is no increase in temperature. Likewise, between these 2 points, there is no increase in temperature. So this one here, we say, since we are putting in more heat to this ice, but it's not causing the temperature of the ice to increase, we say that heat is hidden, okay? Because you are adding heat, but you don't see what is doing. So it is hidden heat. So in science, we call it latent heat of fusion. Okay. So this one here, it is the latent heat of fusion. Now, the word latent is the Latin one, which means hidden. Okay. So we are talking of the heat which we are adding to the substance, but we don't know what it is doing. It is not raising the temperature of the substance, so as if it is just hidden somewhere. So that's why we call it the latent heat of fusion. Then at this point here, we call it the latent heat of vaporization. So this is latent heat of fusion, that one is latent heat of vaporization. Okay. And I explained these 2 words. I said to fuse in science means to turn from solid state to a liquid state. And we also gave it a name, melting. So if I heat a substance, for example, ice is in the solid state. If I heat it until it melts, okay, we say the ice fuses. Or if I heat sodium chloride, common salt, until it melts, we say the sodium chloride is fused. Okay. So it's from the word fuse. I know the other time somebody was trying to say, but fusion has a double S. It is fission which has double S. Fusion has got single S. And it's from the word to fuse, F-U-S-E. And vaporization is from the word vapor, vaporize, turn from liquid into vapor. So those ones we saw. Now, when we came to the cooling curve, this was the heating curve. Now, I requested you to draw the cooling curve. Okay. That means I expected you to begin from a high temperature, which represents the temperature of steam. So at time t is equal to 0, at that time, you begin from a very high temperature, that would be the temperature of steam. Now, when you cool it, when you start cooling that steam, as time goes on, the temperature will drop until such a time that that steam begins to turn into liquid. So I expected you to again make this one here parallel to the horizontal axis, the time axis. meaning that the temperature remains the same when the steam is turning into the liquid water. Then when all the steam has turned into the liquid water, you will see the temperature again dropping. As you cool it, it drops. And then it reaches somewhere, it will reach somewhere possibly at 0 degrees centigrade, and then you will see it again, the temperature becoming constant. So it will again become constant for some time until all the water has turned into ice. Here you have steam. Here you have steam turning into water. Here you have water cooling. Here you have water turning into ice. Then if you cool it further, if it were possible for us to cool it further, then that ice is going to reduce in temperature, and possibly until you get to a lower temperature as low as minus 25 degrees centigrade. So you can see that this one here is the opposite of this. Okay. Now, my question is, what do you think is the application of vaporization, for example? Where can we apply vaporization? When a substance is turning into a vapor, it cools. Okay? And where in life have you ever seen that being used or being applied under normal conditions? I will allow Bukenya Alia. You have, let's see Gloria. Gloria, I want, yes, please, you are breaking up.
I wanted to give a contribution last time.
Okay, who is that one? Say your name.
Gloria.
Okay, right. Go ahead, Gloria. Hey, you are lost. We have lost you. How about Bukenya Alia?
Distillation of alcohol.
Yes, please.
Distillation of alcohol. Like that's where
that is wonderful. Okay, when people are distilling the alcohol, they turn the vapor into first of all they turn the liquid into vapor, and then they condense that vapor back to the liquid alcohol. Okay. Now there is a reason for doing that. Okay. Now even when we, of course, now we are trying to, they are trying to build a pipe for the petroleum, which is going to be mined in around from Hoima. They are doing a pipe which is going to take that oil somewhere in Tanzania for refining. So when we are refining that petroleum, what do? They heat it, and then they again condense the vapor into different substances like petrol, like diesel, like kerosene, and so many others. That's why we have different fractions for from the same petroleum or from the same substance. Now, the petroleum, before it is distilled, we say it is crude. Okay? It is crude, meaning it is not pure. It is crude. But when we distill it, then it becomes some problem. Sorry about that. Sorry about the interruption. So I was talking about the crude petroleum. So in the same way, when people are distilling in villages, for example, they boil the crude liquid, and then that liquid is turned into the alcohol. Now, I want to give you a simple. I want to imagine that you people at home, you have the sanitizer. At home, you have the sanitizer, and you know what it does. Now, I want you to just get a very small amount of that sanitizer, and then you put a drop of it or a few drops on the surface of at the back of your hand. When you have put it there, possibly if it is not very concentrated with the alcohol, then to get the feel of what I want you to feel, you can just wave your hand around or move your hand around, and you'll be able to sense something that happens at that area where you have placed the few drops or the drops of the sanitizer. Okay. Now, what happens is that can you see your hand is up? Can you see?
Teacher, about that vaporization, is it the same as evaporation?
There is no difference. There is no difference. There's no difference. We are talking about the same thing. The turning from the liquid state into the vapor state. Now, the only difference can be in terms of not necessarily. It will be in terms of, for example, if I'm heating water at 10 degrees centigrade, it will be able to turn into vapor. You will see the vapor coming off. At the same time, if I'm heating the water at 100 degrees centigrade, you'll be able to see the vapor coming off. But that vapor at 100, we call it steam. Okay? But still, it will be the vapor anyway. Right. So that is now. What happens is that when you are adding, or when you put the drop of that sanitizer on your hand, at the back of your hand, remember our body temperature is about 36.7 degrees centigrade, or 36.9 degrees centigrade. Though some people may have temperatures which are below that, but that is the average. Okay? Because when we are taking body temperatures for you people when you are in school, at times you find somebody has a body temperature of 34, others have 39, others have 37. So the range, this is I've taken the average. Okay? So when you put a drop of the sanitizer on your hand, that means that sanitizer usually is at room temperature, which is about 20 degrees centigrade. So when you put it on your hand, that means that your body is going to supply heat to that sanitizer. And when it gets heat, what happens? The molecules of the sanitizer will now begin evaporating. They will turn into vapor. And within no time, you will not see the drop that you put on your hand. The drop, the drop of the sanitizer. Within no time, it will not be there. And where has it gone? It has turned into vapor. But as you move your hand around with the drop on, or as that evaporation takes place, that turning from the liquid state into the vapor state, you will be able to feel some coldness at the spot where you put the drop. And it works best when you have spirit. When you have spirit, like methylated spirit, it works best. When you put it there and you leave it for some time, you will see the spirit disappearing. Okay, and as it disappears, that place feels very cold. The place where you put it, it feels very cold. Okay?
Even the spirit they put in the salon, as it disappears, you feel cold.
Okay, even when Adikin is telling us that even when you go to a salon for putting right your hair, when they apply that spirit, you are able to feel that that effect that I'm talking about. Now, why do we feel that effect? We feel that effect because as the molecules of the spirit leave the surface of the skin into the vapor state, as they leave the surface of the skin to go into the vapor state, they gain energy. Where are they getting that energy from? From your skin. And when they get energy from the skin, it means that the skin where they are getting the energy from must become cold or more cold than it was initially. And that is why you feel cold when you have put a drop of spirit or a drop of the sanitizer on your hand, on your skin, and then you leave it for some time. It evaporates, and as it does so, it carries heat from your skin, and that heat is supposed to turn the molecules of that liquid into the vapor. Now the question, another question would be, what is, or where do we find an application of that effect? Is it important to us? Yes, it is. For example, I have just said that our normal body temperature is about 36.7. But when you do something, when you do an exercise and you sweat, what happens is as the sweat leaves your skin, the temperature of your skin is kept at that 36.7. If it varies, it may not vary by more than 2 degrees centigrade. So we are able to have the temperature of our bodies regulated at almost a constant temperature. So when the day is very hot, you may experience some sweating, and as you sweat, the temperature of the body will be maintained because the sweat will be taking away part of the heat as it evaporates or as it turns from the liquid state into the vapor state. So it is very important for some of us to, for you, for example, to take note of some of these natural phenomena which occur to us, though we are not conscious that it is happening. For some of you are going to become doctors. When a patient comes to you with a temperature which is about 40 plus degrees centigrade, then you should be able to know that that patient must be having a problem. Otherwise, the body temperature must not go beyond this one very much. So that is how we can make use of this process to regulate our, of course, it is God who did it that way. I'm not saying that a human being is able to regulate. No, it's God who designed it in such a way that that evaporation can cause or can make the temperature to be relatively constant. Then I want also to talk about something else. Supposing you get, I don't know which gas you know, the gas that you know of, which smells very badly. In chemistry, we have one. There's a gas called hydrogen sulfide. That gas, if you found it in a room, you will not like staying there for even 1 second. One, it is poisonous, and two, it has a very, very bad smell. If you have ever reared a chicken, a hen, when it incubates on the eggs, it takes about, I think about 21 days. When a hen has laid eggs and starts incubating, it takes about 21 days for the eggs to hatch into chicks. Now, if one of those eggs was not fertilized, it means that egg will not hatch out into a chick. Now, if you want to see, or if you want to know how the hydrogen sulfide smells like, get that egg which the hen has been incubating on and it has not hatched, and then you break it. You'll find inside there will be a funny liquid inside, but the smell that comes out of it, of that liquid, you cannot tolerate it for some time. So that smell is characteristic of the smell of the hydrogen sulfide. It has a very bad smell. Now, supposing you broke that egg inside your house or at home, and then you put it at one corner of your room. The moment any other person enters that room, even when that person does not go to the point where that egg was broken from, that person should be able to sense that bad smell of that rotten egg. Now, what does that mean? It means that the particles come from that region or that area where the egg was broken from, and then spread all over the entire room. That is why the person who enters, even when you are entering a door, or you are entering through the door, you are able to sense that smell because it has spread from the region where it was concentrated to the regions where it was less by the process that we have identified as diffusion. We say it has diffused. Now, even at home, when you are cooking, when you are cooking a nice meal, you'll see even the neighbors will start salivating. Even if you have the dogs around, they will start salivating, and it is hard to discipline them, because they will be sensing that nice smell coming from the food that you are preparing. So there are so many things that we can talk about that explain the particle nature of matter, so that we can be able to explain them when that time comes. Now, I want to give a chance to somebody whose hand is up. That is, I think, Karema Shadia. Karema, you, yes, please. Karema cannot hear you. It looks like you have a problem with your mic. Can we hear from Amina? Your hand is up, Amina.
Excuse me, teacher. Is there like any matter which does not vaporize or evaporate?
That's an interesting question. I want to say that it will depend on how you subject that piece of matter that you are talking about to various conditions, because we said that even water is made in solid. Okay, water is in the solid state as ice. Okay, but when you heat it, it will melt. After melting, it will evaporate. So in other words, water can evaporate. When we talk about the sodium chloride, the common salt that we normally use when we are at table, the one we put in our sauce, that sodium chloride, when you heat it, when you heat it, it also melts and becomes liquid. Now, when you continue heating that liquid sodium chloride, it will also turn into vapor. Okay. So it doesn't mean that that it's only the water that can be made to evaporate. Even other substances can do the same. I hope that is clear.
Teacher,
yes, please.
I think I didn't hear properly when you explained the part of sanitizer, why it's called when you put it in.
Don't worry, I'll do it again. Now, possibly the sanitizer, I use the sanitizer because the sanitizer is something that is commonly known by almost everybody during this time of COVID-19. Okay, everybody knows about the sanitizer. But if you have spirit, like methylated spirit, it can also work best for you. Just get a few drops of spirit and you put it at the back of your hand. Okay, just a few drops, and then you wait for some few minutes. You'll be able to see that your skin, that place where you put the spirit, it will be dry without anything. Where does the spirit go? It means it has turned into vapor. Okay. Now, as it turns into vapor, what happens? It gets the energy, the heat energy from your skin. Now, when you are getting energy from something, or when you are getting heat from something, what happens? That something must be able to cool. If I put water, let's say warm water in a refrigerator, what am I looking for? I'm looking forward to seeing or to having that water becoming more cold than it was. So what the fridge does is to remove that heat that was in the water. So similarly, if these particles of spirit which you put on your skin, if they are to evaporate, okay, where do they get the energy from? They will get the heat energy from your skin. Remember, your body temperature, we say, is about 36.7 or 0.7 degrees centigrade. That is your body temperature. Now, the spirit that you are using is at room temperature, which may be at around, let's say, 25 degrees centigrade. Now, if you put two bodies which have got different temperatures near one another, what happens? The cold body gets heat from the hot body, and the hot body loses some of its heat to the cold body. So even when you put a drop of spirit on your hand, what happens is your hot body or your warm body is going to lose part of that warmth to the spirit, which is at a lower temperature, and therefore the molecules of spirit will evaporate, will gain that energy, they become more energetic, and they escape into the vapor. And as they do so, that point where you put the spirit becomes cold. Why? Because the particles or the molecules are extracting the heat energy from that part of the body. So that's why you feel cold. Or that part of the body feels very cold as the spirit evaporates from it. I hope it is understandable. Right, so that is, I just brought in the sanitizer because it is the one which is very readily available. But even the spirit can work very well. Spirit can work, even ethanol can work because the sanitizer is about 80% ethanol. It can also work very well. So we have very many other things that we can use for showing that actually matter is made up of particles. And the last thing I want to share with you possibly is I don't know whether you have ever heard of something called a cool drink powder. When you look at your workbooks, there is a mention of that cool drink powder. It has that cool drink powder, and when you put that powder in water, and then you stir. Why do you think when you taste that water, it tastes sweet? That means that the particles of that that powder have spread from where you put them into the entire water in the glass, for example. So that even when you put sugar in a cup of tea, when you put sugar in a cup of tea and then you stir using a spoon, what happens? When you taste that tea, it is sweet. Now, why does it become sweet? It's because of the sugar that you have put in. Because if you just picked a few crystals of sugar and you put it in your mouth, on your tongue, you will feel that sweetness. Even when you put it in water and you stir, or in a cup of warm water, or in a cup of hot water, which you want to use as tea, and you stir, the cup of tea will be sweet. That shows you that the sugar particles have spread from where you put them into all other parts of that of that tea. That's why the tea becomes sweet also. Okay. So there are numerous examples that we can talk of or that we can give, but I'm just giving you a few of them, just a few. But there are so many examples out there. So there are so many examples out there which we can use. So my giving you these, I think I've given you about 5 or so examples of the evidence for existence of matter. But out there, you should be able to generate more examples. Okay, you see, what the teacher does is we guide you. So I have guided you as to what evidence we can use to show that matter is made up of tiny particles and they are constantly in random motion. So having guided you with those few examples, we expect that you go an extra mile and find out more examples that we can use, that you yourself can use. Because when you use those examples, when you identify those examples yourselves, you will be in position to understand the concept much better. Because if we are not, your curriculum is different from the previous traditional curriculum, where the teacher knows it all, and then we give you everything. No, here, the student plays a very big role in that. The teacher just energizes the student, and then the student gets to get more information on his own or her own. And that is the nature of the new syllabus, or the new curriculum, rather. That is why we should be able to, for example, the internet has got the internet, you see, has a lot of things, a lot of things. However, some of us are misusing those gadgets. I mean, those things, because we would like you to use things like the YouTube. Use it correctly for getting the information. Okay? The YouTube, the internet, the Google has so many things. Okay, we want you to use those things to enrich yourselves with knowledge. Okay.
I have a question.
Yes, please.
Why does the fusion move faster in gases than liquids?
Okay, somebody is asking, why does diffusion happen faster in gases than in liquids? Now, remember what we said about the arrangement of the particles. That is the one that makes or creates that difference. In liquids, the molecules are they are not very close together, as in solids. But when it comes to gases, the molecules or the particles are very widely spaced. So it means that when they have enough space where they can move, they will move faster. But in liquids where they have a smaller space, their movement will be somehow restricted. And even in solids where they have virtually no space, their movement will be
Teacher, I have a question.
yes, please.
When I was home, my name is Marilyn Owing.
Yes.
When I was home one day, I mixed a sanitizer and liquid soap, and it formed a bit of heat. Can you please explain where that heat came from?
Now, you see, chemical reactions. There are those chemical reactions which happen with loss of heat, and then there are those which happen with gaining of heat. For example, if I gave you concentrated sulfuric acid and I said, just put a few drops of concentrated sulfuric acid in water, and then you get hold of the container in which that mixture is, you'll see that it has become hot. Why? Because that reaction of dissolving the sulfuric acid in water is, the other time we say, exothermic. An exothermic process. However, there are also some substances. For example, if I gave you a salt like potassium nitrate, if I gave you potassium nitrate, and I gave you a small amount of water in a beaker, I gave you a thermometer, and then I said, put potassium nitrate in that beaker containing water and stir. If you touch that beaker, it will be much more cold than it was initially. What does that mean? It means the potassium nitrate, when it dissolves in water, it absorbs heat. So the process is endothermic. Exothermic means giving out heat. Endothermic means gaining heat. So when you mix the, I don't know what your intention was. When you mixed the sanitizer with the, you said liquid soap?
Yes.
And there was, you registered some warmth. That means that is a reaction which is exothermic. It gives out heat. Is a reaction that occurs. But of course, these particles are so tiny, you cannot see that they are reacting. Okay? You can't see, but you'll be able to, it will be manifested in form of the heat. So that is what could have happened. I want very pleased. Though you should not, especially if you come to the lab.
Excuse me.
It is a chemistry lab.
Excuse me,
Don't mix things anyhow, because you can create an explosion. Okay? Because you don't mix. I remember one time when I was planning to become a teacher, we had a student teacher who was after doing an experiment with the sodium and potassium, showing the students how reactive they are. Now the teacher picked a very tiny sample of potassium and dropped it in a beaker of water. Now these students got excited. They saw how the flame was created and how it was dancing on top of the water. Then the teacher made a mistake. The student teacher made a mistake and left a bottle of potassium in front of the classroom, in front of the lab, when the bell for break rang. So everybody went out. The teacher also went out. Now some funny student came back and said, I think this teacher was joking. Now got a very big piece of potassium, this size, and dropped it in a sink, then opened the tap. We were in the staff room, and I'm not saying it was here, but it was in another school where I was doing my school practice. The explosion was as if there was a bomb that was dropped in the school. So when you are in the lab, you avoid mixing things anyhow. I know you are curious to mix a sanitizer with the with the liquid soap. But in the lab, you don't have to do that unless you request that you want to do this, and then we advise you accordingly. Okay, so we are going to stop at this. We just wanted to emphasize the evidence for the particulate nature of matter, that matter is made up of particles. So tomorrow when we meet, we shall proceed from there. Thank you for attending.